All right, this lesson is also out of place, but whatever, we got to do it in the order Blyth does. I usually include this in its own separate unit at the end of the course, but who am I to complain, right? We have this thing called average rate of change. An average rate of change is really just code for slope. The average rate of change is the slope between 2 points on a graph. Any 2 points, doesn't matter. They'll tell you which points to use. Here's my example. What is the average rate of change, i.e. the slope, of this projectile from 7 seconds to 11 seconds in the graph below? To find the average rate of change, all you need to do is find the slope. Your formula for slope, if you remember it, is y2 minus y1 over x2 minus x1. And what's awesome about average rate of change is you're often going to be given the points. Here's point 1, here's point 2. So I have my x1 here and my y1 here. This is my point at x equals 7, see? And I'm going to x equals 11. Oh, that's this point here. Whoa, this curve wasn't even in the right place. Whatever. And this is my x2 and my y2. And all I have to do is plug these points in and get the slope between them. It's the easiest thing in the world. y2 minus y1 over x2 minus x1. Now I'm going to need a calculator for this. Where did I put it? Oh, it's right over here. 277 minus 350 gives me negative 73. 11 minus 7. I probably could have done that in my head. And negative 73 divided by 4 gives me negative 18.25. I'm probably just going to leave. Yeah, negative 18.25. So my average rate of change is negative 18.25. Now, my units on that is y over x. It says here that my y is height in meters, and I was told that my x was time in seconds. Now, what this means is that I'm losing, on average, 18 meters of height every second the projectile is in the air. It's an average rate of change. It's descending slowly here, and then it's descending faster here. I picture this to be like a ball you throw up in the air, and you throw it up, apparently 300 meters in the air, and then once you get up here, it kind of stops for a second. It's at its peak, and then it starts falling back to the ground. And when is it traveling fastest? Just before it hits the ground, because gravity makes it go faster and faster and faster and faster and faster. Same reason if you dropped a penny off the CN Tower, it could kill someone. It's just traveling so fast because it fell so far. My point is, if they ask for average rate of change, they're looking for the slope between 2 points, and it's the easiest thing ever. Okay? So the average speed of the projectile from 7 to 11 seconds is negative 18.25 meters per second. Pretty sweet. Now, that slope that we found is actually the slope of the line that connects the 2 points. Now you'll notice that line hits the curve in 2 places. That makes it a secant. A line that connects 2 points on a curve is called a secant. A secant divides the curve into 2 or more pieces. See? Piece 1, piece 2. And it touches the curve in 2 different places. Secant is different fundamentally from a tangent. Tangents are coming up later in the course. But secant, again, cuts the curve in 2 places. I thought about telling you what a tangent was, but it doesn't really matter at this point in the game. So let's move on to the next page where we have this last thing called instantaneous rate of change. Not average, instantaneous. Now, the instantaneous rate of change is not between 2 points on the curve. You're looking for the speed at a particular point at exactly 11 seconds. we can estimate what this is. There are other techniques for finding it. That's for calculus, not for advanced functions. You're only responsible for this. To find the instantaneous rate of change, I want you finding average rate of change between 2 points that are super close together. If I want my instantaneous rate of change at 11, I choose 11 and 11.1. Now, this is going to take a little bit of work, so bear with me. What is the height at 11? Well, they gave me that. The height at 11 was 277. Oh. Did I even write the function down? I did. I wrote the function here for you. We didn't use it, but we will here. So, at t equals 11, my y is 277. So I have 11, 277 as 1 point. Now, to get my second point, I have to plug 11.1 into my original function. I need the height at 11.1 seconds. My function is negative 4.9t squared plus 70t plus 100. Negative 4.9 t, that's 11.1 squared, plus 70t plus 100. Now I just need to put that into my calculator. 11.1 squared times negative 4.9 gives me negative 603.73. 11.1 times 70 gives me 777, and I add 100. Now I have to do all the... I'm just doing regular grade 9 math right now. Just plugging this 11.1 in. Plus 777 plus 100. You probably did this faster than me. 273.27. Great. Now this makes sense in that at 11 seconds, I'm 277 meters in the air. And at 11.1 seconds, only a tenth of a second later, I've only fallen, 3.7 meters. Not much time goes by, not much difference in height. But I do want you to find the average rate of change between these 2 points. Do you remember how to do that? y2 minus y1 over x2 minus x1. y2, 273.27 minus 277 over 11.1 minus 11. It doesn't matter what order you put your 1s and 2s in as long as you keep it the same. 11 corresponds to 277, so they're both last. Now I got to do this. 273.27 minus 277 divided by, I can do that in my head, 0.1. I get negative 37.3. Negative 37.3. And remember, your average rate of change is your unit on y over your unit on x, meters per second. So it seems to me that between 11 and 11.1 seconds, I'm descending by 37.3 meters per second. That is way different than the average rate of change from 7 to 11. But remember, as you continue to fall, you continue to move faster and faster and faster. So you should be faster at 11 than you were on average between 7 and 11. Now, in order to estimate the instantaneous rate of change, I want you to do it a second time. And sometimes teachers will ask you to do it a third time as well. I'm going to skip straight to the end here to demonstrate how to do it. Again, you just need your x1, y1, which is exactly the same because you want it from 11. But now you want it from 11 to 11.001. That's super close to 11. To estimate my y at 11.001, I have to plug it in. Negative 4.9, 11.001 squared, plus 70 11.001s, plus 100. Now, for this particular example, when you do instantaneous rate of change, I want you carrying every single decimal place that you can through the calculation. I don't want you rounding it all until the very end. The reason is, A tiny bit of rounding, even in the millionths place, can throw off your numbers here. So let's do this all at once. 11.001 squared times negative 4.9 plus 70 times 11.001 plus 100. 277.0621951. Notice I just kept all of my decimal places. That's how it goes. And now that I have my y that corresponds to this second x, I can plug them in to my average rate of change formula. y2, oh, that's not y. y2, 0621951, minus y1 over x2 minus x1. Notice that my y2 is super close to my y1. In that thousandth of a second difference, I only descended 6 centimeters or whatever, 0.06 of a meter. That's not what matters, though. What matters is that I can do this on my calculator. Minus 277. Notice I'm left with 0.0 something. This is why I don't want you rounding, because you end up having all these extra decimal places of zeros. And if these numbers are off, it can throw everything else off. And then I divide by the difference between these two, 0.001. I get, oh, well, that's weird. I was expecting a number slightly less than this at 11.001. Damn it, I need to do this calculation again. 11.001 squared times 4.9, negative 4.9, plus 70 times 11.001, plus 100. Damn it. Why am I getting a number slightly bigger than 11? Than 277, I should say. 11 squared times... Man, I'm going to have to redo this whole video if this doesn't work. Oh, crap. It's 11,277.1, and I rounded it for the purposes of this and then didn't include it later. Well, damn it. Okay, so this was supposed to be 11,277.1 the whole time. But, I mean, it doesn't really affect this. I guess it puts this off by 0.1 or whatever. But let me just do this calculation to finish this off. It's the most embarrassing thing that's ever happened. 1951 minus 277.1. Damn it. Can I not even type anymore? 277.0621951 minus 277.1. Good. Negative, because it's falling. Divide by 0.001. Good. Negative 37.8 meters per second. Good. So, what you'll notice is that, now I know this number is wrong, but bear with me. As the 2 points we choose get closer and closer together, 11 and 11.1, 11 and 11.01, 11 and 11.001, the closer the average rate of change gets to becoming the instantaneous rate of change. It looks to me, negative 37.3, negative 37.8, that I'm becoming closer and closer to negative 38 meters per second. So I'm going to estimate that my instantaneous rate of change is about negative 38. Let me emphasize that with English words. The average rate of change seems to be approaching negative 38 meters per second as the two x values get closer together. And we estimate the instantaneous rate of change then to be about negative 38 meters per second. To get IROC, instantaneous rate of change, you just do average rate of change for 2 points that are freakishly close. and you carry the decimal places because you don't want to make rounding errors. 15 minutes. Bam, best of luck.